So note down all the inlet side at section 1, the parameters considered for the Bernoulli's equation and continuity equation, and section 2, which parameters are considered for the Bernoulli's and the continuity equation. Then first thing is to apply the Bernoulli's equation, or first you can start with the continuity equation also. But there we don't have many terms. We have only A1, V1 and A2, V2. So I think all of you understood these steps. So from the Bernoulli's equation, after simplification, that is because of horizontal pipe or the horizontal device, Venturimeter is connected, Z1 equal to Z2 we are considering, or we are cancelling Z1 and Z2. Then difference of pressure head, that is P by rho g, if you consider effective pressure P by rho g, that you can replace with head of the water due to change in pressures. That you can write on the left hand side. Right hand side we have left with difference of velocity square divided by 2g. This is from Bernoulli's equation. Now going by continuity equation, okay, we know that discharge can be written as QA can be written as A1 V1 equal to A2 V2. All of you know this term. Now from this either you can take V2 or V1. So for my reference I have taken V1 equal to A2 V2 divided by A1, or you can write V2 equal to A1 V1 by A2. This is just for our reference. You can take any one. Okay. So as I have taken V1 here, so V1 I know now. From the continuity equation, we can substitute V1 as A2 V2 divided by A1. Can be substituted in the above Bernoulli's equation, that is equation 1 after simplification. If I substitute that, I can write it as V2 square minus, what is V1 now? V1 from the continuity equation can be written as A2 V2 divided by A1 whole square divided by 2g. So this is shown in the below step. So just we are replacing V1 term with V2, so that in the simplification we can take only one velocity term, that is V2. So from this step what you can do now, in the numerator we have V2 as a common term and 2g in the denominator we have the common term. So taking this V2 square divided by 2g as common term, I can write it as V2 square minus 2g common into bracket. The first term will be 1 because entire term from the first is taken out. 1 minus, we left with A2 square divided by A1 square. We left with 1 minus A2 square divided by A1 square. Now taking this V2 square left side, H on right side, just replacing V2 and H values or the H terms on the left and right hand side. We can write it as V2 square on the left hand side equal to, okay, equal to 2gh into A1 square by A1 square minus A2 square. So in the above equation, you can take the LCM for 1 minus A2 square by A1 square. So you'll get the value like A1 square minus A2 square divided by A1 square. So once you replace this H term and V2 square on the left hand side and right hand side, now we can write this equation. V2 square equal to, so H will be multiplied with 2GH. Okay. So these terms will be in the numerator. That is 2GH into bracket, you can write A1 square divided by A1 square minus A2 square. So as it is square term here, V2 square, I can write it V2. So now the entire term will be in under square or the square root, under square root. Later you can remove that square root for some of the terms. You are following the steps here. All of you are understanding the steps of Venturimeter derivation. Okay, same steps we are again using for the orifice also. Okay, same steps we are using for the orifice with one of the extra term which is introduced in the orifice. Okay. So from V2 square, I can write it as V2 taking square root for both the sides. I can take square root for both the sides so that I can write V2 as square root of 2GH into here A1 square divided by A1 square minus A2 square. Just exchanging the numerator and denominator in the above step. And once you try to remove this square root, what we can do now, I can remove the square root for only A1 square. I can write it as A1. A1 square minus A2 square is a combined term. So I cannot remove it. I'll write it as square root of A1 square minus A2 square as it is. And square root of 2GH. This is very important term now. Square root of 2GH. We are using this in many problems now. Square root of 2GH. So keep in mind, this square root of 2GH we are keeping on the other side. So this becomes our V2 value. V2. What is V2? If you don't know V2 or velocity in the pipe, still we can find the discharge by the Venturimeter and the orifice meter. That is the one of the uh, advantage of using these Venturimeter and orifice, because we need not to have velocity also for this finding discharge. If you know the areas, if you know the head, one can find out the discharge without knowing the velocity. So now what I'll do, by using this V2 value, I'll substitute in the discharge equation, because finally we want to find out discharge. Now discharge we are finding in two terms. One is theoretical discharge. This is the theoretical discharge. Q equal to A2 V2 into A1 V1 is the theoretical discharge. Now for actual discharge, we need to find out that coefficient of discharge. How much is the loss taking place in any given devices or any given pipes? Once if you go by that losses or the coefficient of losses, that I can substitute here and I can find out actual discharge. So all of you already know the discharge, how to find out. So if you go by V1 value, as I told you, if you go by like this, if you go by V2 equal to A1 V1 by A2, if I find out, later I can find out for V1, what is the value of V1, I can substitute in this equation. Later I can find out A1 V1, what is A1 V1 by this equation. But here in this step, I have gone by V2, finding V2, and A2 is already known by the diameter. So what I'm doing here, I'm taking this equation, A2 V2 equation. So I'm multiplying A2 into A1 by square root of A1 square minus A2 square into square root of 2GH. So that is multiplied here. This itself is the velocity. Velocity term is this entire bracket into area 2. Now we have found out the theoretical discharge equation for the Venturimeter. So that equation you can call it as equation number 2. Equation number is 1 is for H equal to V2 square minus V1 square by 2G. Now second term, from the continuity equation, Q can be written as A1 A2 divided by square root of A1 square minus A2 square into square root of 2GH. This all of you know from the lab. How you came to this equation? By using Bernoulli's equation and by applying the continuity equation. So this equation is called as theoretical discharge. Theoretical discharge from the Venturimeter or the orifice meter. So that you can write equation 2 represents theoretical discharge of the flow measuring device. It may be Venturimeter, it may be orifice meter. Now to find the actual discharge, we know one more relation. That is coefficient of discharge for orifice or the Venturimeter is given by, you can write down CD equal to Q actual by Q theoretical. Coefficient of discharge for the Venturimeter and orifice can be shown as, or it is the ratio of actual discharge to the theoretical discharge. That is the definition of coefficient of discharge. This is the definition, CD. CD is Q actual by Q theoretical. That's why now we can write Q actual equal to coefficient of discharge of Venturimeter into Q theoretical. So what is Q theoretical? We found out that Q theoretical is A1 A2 divided by square root of A1 square minus A2 square into square root of 2GH is the theoretical. By just by using the dimensions we are finding this theoretical discharge. Later, if you know the losses, how much loss is taking place because of the fitting of Venturimeter or the orifice meter, if you know the losses, now considering those losses, one can find out this CD value and he can substitute here. So by considering the losses, if you find out, one can find out the actual discharge. How much actual discharge is coming from that pipe. So that's why we are just multiplying the CD value with the theoretical discharge equation. Or it is multiplying of CD into equation number 2. So this coefficient of discharge, you can see here, always the theoretical value will be higher and actual values will be less. So what happens? The value of CD will not cross one value, or it may not be 100%. Okay, so this CD value, or after considering the losses, so 100 minus that losses, if you consider, the losses will be in the range for the Venturimeter will be up to 0.94 or 0.98. It just represents the accuracy of the Venturimeter. This is not given in the derivation or the theoretical part. This you are finding in the lab and you are finding what is the CD value of the Venturimeter. So that ranges from 0.94 to 0.98 for the given converging and diverging angles. This you have to maintain properly. If the converging diverging angles are differing, then the losses will be high. So for optimum losses or the very less losses, what will happen? It may be working under 94 or 98% accuracy. That indicated by CD. For orifice, if you go, the value may be 0.6 or 0.65. Means losses are 40%. Okay, out of that 40% losses, we are considering only 60%. 60% or 65% is the actual flow through the orifice meter. So this is the difference between Venturimeter and orifice meter, where the losses in the Venturimeters are very less, okay, and accuracy of the results will be high. Now, what is the disadvantage of Venturimeter? Can you tell me? Compared to orifice meter, what are the other difficulties in orifice meter or Venturimeter? By seeing the design of that orifice and venturimeter in the lab, can you suggest me any other difficulties with respect to orifice or the venturimeter? So length of venturimeter and orifice, if we consider, which is having the more length? Those who have seen in the lab can reply. Venturimeter, length of venturimeter and the length of orifice meter. Okay, venturimeter length is high because of converging throat and diverging length. If you see, the length of the venturimeter required to be fitted in the pipe connection will be higher. So there will be loss of pipe material, or some length of the pipe is not required. So what happens? The dimensions of the venturimeter will be higher because of the long length. And also designing of this venturimeter will be very difficult. Okay, but keeping in mind the losses and the percentage of error, if you see, the venturimeter will be having very good efficiency for finding the discharge, or the more accuracy of discharge can be found out by the venturimeters compared to orifice meters. But ultimately, we know the CD value. Once you know the CD value of the venturimeter or orifice, everyone can find the accurate values of the actual discharge, but the error will be differing. But error will be more in orifice, error will be less in venturimeter, so that the easily operator can find out more accurate results within less difficulties with the venturimeter compared to the orifice meter. So here design, cost and the dimensions of the venturimeter, if you see, all are higher side, very difficult. But comparing to the orifice meter, it will be having very small dimensions as you've seen in the lab. Now coming to the manometers, how to find this head. So already you know some equations. Same thing we are recalling in the theory also. So if the manometer is using the case one, if you see, if the manometer is using heavier liquid than the flowing liquid, okay. So in such cases, in theory, just representing the units and notations, you can follow any notations as per the lab or as per the theory, okay. Values or the equation parameters will not change. Only the notations and units may be different. So as per that, I am going to represent the specific gravity of the heavier liquid as SH, because in the lab you are using mercury. Every time they are writing density of mercury M, rho M or SM like that. But in the reference of theory, I consider any liquid which is heavier than the flowing fluid. That I represented as SH. And specific gravity of the liquid which is flowing in the pipe enclosed channel will consider it as SP. Specific gravity of the flowing fluid in the pipe. The flowing fluid may be any chemical, water as like in the lab or in civil applications, or it may be a oil in a different oil industries. So like that, specific gravity of the liquid which is flowing through the pipe, that is different. Now X is the difference of the heavier liquid in the manometer, or you can remember difference of the manometer liquid levels, that is denoted by X. If this is the condition, we can find out head in the manometer, okay, not in the pipe. Head of the pipe we are not finding, head of the manometer we are finding, okay. So that head of liquid is X into, that is the level difference in the manometer, X in centimeter or in meters, into bracket ratio of specific gravity of heavier liquid to the specific gravity of the light liquid minus 1. Or if the specific gravity or the specific weight is not given, you can take density of the mercury to the density of the liquid which is flowing in the pipe. That is rho m by rho water in the lab you have seen. So if the liquid is lighter, if in case liquid is lighter in the manometer and liquid in the pipe flowing, which is heavier. In such case, just we are reversing the equation. So for that, we have represented the specific gravity of the lighter liquid as SL in the U-tube, and specific gravity of the flowing fluid in the pipe we have considered as SP, same as above terms. So in such case, if you want to find out the head, okay, so head in the with respect to flowing fluid, I can write it as H equal to X, that is the level difference in the manometer, X value. Here we have to take reverse. If the liquid in the manometer is lighter, that is 1 minus specific gravity of the lighter liquid divided by specific gravity of the flowing fluid, or the flow of fluid flowing in the pipe, that is represented by SP. Already you know these equations. This is one more extra equation where the liquid in the manometer may be lighter. So many cases it will not happen. Maybe in numerical we may give if the manometer liquid is lighter. Now in application what happens is, say for example, water head is around 2 meters. Okay, around 2 meters. By using the lighter liquid, okay, liquid which is lighter than the water, if I am using in the manometer, what may be the head of that liquid? Is it showing 2 meters or above that? If the liquid is lighter. Any answers? If the liquid in the manometer is lighter than the flowing liquid in the pipe, then the head of liquid present in manometer will be showing more than the pipe flow, or it will be same, or it will be less. Yes, it will be more because liquid is lighter. So heavy liquid will be having low heads compared to the lighter liquids. And if it is showing more head, then we need a big manometer of 2 floor or 3 floors, and very difficult to read the readings also. So in such cases, actually in applications, we are not using the lighter liquids in the manometers. So next we'll take some examples or the numericals on this Venturimeters. So you can note down the examples. The first numerical is the horizontal Venturimeter. So once they tell horizontal Venturimeter, Z1, Z2 is cancelled. Horizontal Venturimeter with inlet diameter 20 centimeter. D1 is given 20 centimeter, and throat diameter, that is the smallest opening of the Venturimeter, throat diameter 10 centimeter, is used to measure the flow of oil of specific gravity 0.8. Now Venturimeter is connected between the pipe, and Venturimeter is used to find out the flow rate of the oil which is flowing in the pipe. So pipe fluid is the oil of specific gravity 0.8. So I can consider SP value as 0.8. The discharge of oil through Venturimeter is 60 liters per second. Discharge value they have given. Actually, by derivation, we need to find out the discharge. That discharge, I think they have taken one big tank. They have collected all the oil in that for a meter cube per second or liter per second. They have found out the value. That is 60 liter per second. Then what we need to find out is, find the reading of the oil mercury. See here, find the reading of the oil mercury means this is for the designing the mercury manometer. For designing the mercury manometer for such liquids with such flow rate, what may be the deflection? So how much dimension it should be designed such that it can show the reading of the oil mercury in the manometer. So finally, we need to find out X value, small x value. That is the reading of the manometer, which is using, okay, which is using which liquid have they given? Find the reading of the oil mercury, oil mercury difference manometer. So manometer is containing the mercury, pipe is containing the oil. So as far as the specific gravity of oil is concerned, it is 0.8. Specific gravity of mercury, if you take, it is 13.6. So mercury is heavier. So the deflection in the mercury manometer will be lesser. Very small deflection will be there. So recall the equation of Venturimeter, that CD into A1 A2 divided by A1 square minus A2 square into square root of 2GH. In that, we need to find out H, and using that head, we need to find out X value by applying the manometer equation. Okay. So coming to the finding areas A1, A2. So A1 from this diameter 2 centimeter, sorry 20 centimeter. So all of you know the diameter of the pipe. If it is given, I can apply the circle formula to find the cross section area, pi by 4 d square. So by that I can find out A1 and A2. So A1 is around 314.16 centimeter square. A2 is 78.54 centimeter square. Then CD value in the problem they have given. Take CD as 0.98, coefficient of discharge, or ratio of Q actual to Q theoretical. They have given 0.98. So 0.98 is given, CD value is given. Now discharge. How much is the discharge now taking place? It is 60 liter per second. So convert that into centimeter cube or in meter cube, whatever. So for that, we can multiply with 1000. So that will be centimeter cube per second. So substitute all the values Q, CD, A1, A2, G is a constant. All these values are known. H is not known. So taking H on the other side, you can find out the deflection in the manometer. So please all of you check the values, whether these values are correct as per the substitution or not. So after simplifying, we got the H value as 289.98 centimeter. Okay, head of the oil. Because as per this equation, discharge, we are finding this A1, A2, CD and H, all is with respect to pipe flow. So with respect to pipe flow, head is 289.98. With respect to this head, what is the deflection shown by the mercury manometer? That is different. So to convert this head into deflection in the manometer, we have this equation. That is X into specific gravity of heavy liquid, specific gravity of the flowing fluid in the pipe minus 1. So if some values are not given, so as per the standard, you need to substitute in the equations. Because in this formula, we don't know the specific gravity of the mercury. So assuming the pure mercury is used and it's not mixed with any dirt and other things, so specific gravity of the mercury can be taken as 13.6 here. Specific gravity of the oil which is flowing in the pipe is already given in the problem 0.98, 0.8. 0.8 is the specific gravity of oil which is flowing. So using these values, one can find out the deflection in the manometer. This 18.12 centimeter, what you are observing, this is with respect to mercury. And later, if you want in meters, you can convert this in meters also. So please, one of you check these values, whether they are correct or not. Later, we can proceed to the other problems.
Excuse me, sir.
Yes.
Sir, you took CD value 9.81.
No, no, 0.98.
Yes,
Ah,
sir, but
here.
you took
Yes, yes,
9.81.
yes. This is the mistake. Yes. 9.81 is wrong. It should be 0.98 as per the given problem. So check the H value. 0.98 into this value. So directly G value I have taken as CD value. H is 13.067. Okay. Check deflection in the mercury. Please, all of you check the mistakes in the problem or find the values, correct values you find out and tell the answers in the chat box. Or you can unmute and tell the answers. Because some numericals in hurry or some writing mistakes, I might have written wrong answers. That's why I'm asking for each problem to find out the actual results, accurate results. What is X value? 0.815. 0.815 meters, no? Centimeters, okay. See, all of you make corrections. H value is coming around 13.067 centimeters here. Head of oil flowing in the pipe, 13 point something. And deflection in the mercury manometer after calculation, correct calculations, we are getting mercury deflection 0.815 centimeters. So these are the correct values. Okay, shall we proceed? Others, others, any reply? All of you got the answers? Okay. Okay, next problem we'll take. We'll see how many problems are there. Okay, we'll take next problem also. The inlet and throat diameters, you can note down D1 and D2 for a horizontal venturimeter are 30 centimeter and 10 centimeter respectively. The liquid flowing through the venturimeter is water. So water is flowing in the pipe. The pressure intensity at inlet is 13.734 Newton per centimeter square. 13.734 Newton per centimeter square. That is the pressure intensity at P1. While the vacuum pressure head, see the wordings. The vacuum pressure head means vacuum means we need to take again negative sign here. At the throat is 37 centimeters of mercury. See the vacuum pressure is not given in Newton per centimeter square. So we cannot take the difference directly. But what we have to do is we need to take the mercury head 37 centimeter. Then we need to convert that into water head. Then we can convert that H into pressure Newton per centimeter square. Or you can go by converting this Newton per centimeter square into head of water. Then you can take the difference. And one value is vacuum. So you can take the negative sign for the given value. It is in vacuum. Find the rate of flow. So we need to find out discharge. So in this problem, we are asking Q. Means the regular equation you have to use, but some conversion you have to do with respect to head and pressure. Assume that 4% of the differential head is lost between inlet and throat. So this is the loss. Loss they have given 4% between inlet and the throat. Find also the value of CD for the venturimeter. So CD value is also not given. Discharge value is also not given. These two we need to find out by converting this pressure into heads and considering this 4% loss in the venturimeter at the inlet and throat. So coming to first finding the required terms in proper units. If you go by that proper units, then I can write A1, A2 in meters or centimeter square. By using the pi by 4 d square formula, one can find out area at the inlet and area at the outlet. They can find out. P1 is given 13.734 into 10 raised to 4 Newton per meter square or in Newton per centimeter square as it is. Now next you can see, as I told, pressure head can be converted either in head of water and difference can be taken later, or else you take the mercury head, convert that into pressure head, because we know the relation between pressure and head, P equal to rho g H. You can find P with respect to H or find H with respect to P by rho g. Any one of the formula I can use and you can find out the pressure head. So what they have done here, they have converted this pressure head itself, that is Newton per centimeter square itself, into meters of water. Later they can go for meters of mercury also. So to convert that, we can take that P1 by rho g so that you can find out H. Head we can find out. That is 13.734 into 10 raised to 4 Newton per meter square divided by density of water, because the fluid which is flowing in the pipe is water. So we have taken 1000 here for the density. Gravity is 9.81. So one can find out what is the head of water. That is 14 meters of water is flowing in the pipe. Head of water is 14 meters. Now next is mercury deflection or the head of mercury. 1 minute. In question, what they have given? While the vacuum pressure head, okay, head is given, not the deflection. Vacuum pressure head is 37 centimeter, which is vacuum because of the mercury. So head is given means I can write it as P2 by rho g. This is not deflection, this is not X value. So due to vacuum pressure, they have taken negative sign here again, minus 37 centimeter of mercury. So this you convert in meters of water. So to converting that, we can go by again specific gravity of the mercury. Okay. So to take that value and convert that into meters of water. So what we have to do now, we have to just convert this centimeter to meters by dividing by 100 into specific gravity of the mercury. If you multiply, one can be able to convert this mercury head into water head. So water head is coming around minus 5.032 meters of water. So please check these values. Why they are converting this pressure, deflections or the pressure values into head, because in the venturimeter equation, we don't have P1, P2 values directly in the equation or in the formula. But in the formula, we have that square root of 2gh, where h value is required. Are you understanding? So for the venturimeter formula, if you see, we need the head value. So they are converting these all pressure values or the pressure head into h values. So once you know the h value, I can substitute in the venturimeter. So please check this pressure head in pipe and pressure head with respect to mercury with vacuum. H equal to 0.0073 mm. For same problem or earlier problem? Yes, Pushpa. H is 0.0073. Is it for earlier problem or same problem? Point 0073. And for which value? Others? For this problem, how much H value you are getting? H in pipe and head of water in manometer. Converting that manometer head of mercury to water head. If you convert, what is the head of water? You can tell in mm or meters or centimeter, anyone. Please, all of you utilize this time to calculate the values. (19.032). All the substitution is correct. Meters of water. Okay. So if all are getting same result, then we'll take the next step. So next step in the Bernoulli's formula, earlier I have told you the head loss, how to consider this head losses. So this is the total head, okay, total head of water which is flowing in the pipe that is 19.032 meters of water, what is possible, that is found out. Now in this 4% loss is there. So that 4%, what you have to do now, you can multiply with this 4%, that is 0.004, you can multiply, and one can find out this 0.7613 meters, that we have to subtract from this total head loss. Okay, so this head loss, or you can recall it like a theoretical head loss, is 19.032. Now considering in actual flow, 4% is the loss. So from this 19.032, you remove the 4% of value. That 4% of value is 0.7613 meters. Once you remove this value, I will get the actual head loss. So that can also given by this formula, square root of h minus hf divided by h. So why they have taken square root directly? Because here you can see in the formula, we know that the CD can be related with respect to h in terms of square root of h, not directly as h. Okay, so to find this, or with respect to CD, if you see the values, I can take this h value, or this the discharge value. If you see, I can relate this discharge with respect to CD directly. But h value, if you want to relate, I have to relate with respect to square root of h, because it is proportional. Discharge is proportional to square root of h. So what they have done? They have taken here h value in terms of square root. So square root of h minus hf. Hf is the loss. With loss, how much is the value? 0.7613 is the loss. They have considered minus that value. This will give us actual head loss divided by theoretical head. Theoretical head is 19.032 meters of water. So please check this CD value, how much you are getting. So as per this problem, CD is given indirectly with the losses. So considering those losses with actual and theoretical by taking the ratios, one can find out these values. One more question may be how to remember this equation if you don't know the uh, CD with respect to this square root of h minus hf divided by h directly. So what you can do, again you can recall the discharge equation from the Venturimeters, that is actual discharge equation. What you can do is, for this actual discharge and theoretical discharge, okay, all A1, A2, 2G values will be same. Are you understanding? All these A1, A2 values will be same. The difference will be only H value. Or with respect to CD, if you talk, only these losses of head and CD values may be different for the actual discharge and the theoretical discharge. So if you take the ratio of Q actual by Q theoretical, I'm taking the ratio of CD into this term divided by this A1, A2 divided by A1 square, A2 square under square root into square root of 2GH. So what we left with after taking the ratios, we left with CD and square root of H. I hope you are getting. Then if you take the equation of this CD with respect to H, I can write directly like this. CD can be directly written as square root of the actual losses of head divided by theoretical losses. That becomes, after simplification, square root of H minus HF divided by H. Okay, CD value is 0.979 or 0.98. Okay, you can consider that value. and substitute that CD value in the main equation. That is in this equation. Q equal to CD into A1 by A2 square root of 2GH, you can find out. So we know H value, we know CD value, we know area at inlet and throat. One can find out the discharge. So I think in this problem, there is no mistakes in finding the results. So I think the Q theoretical value you may get around 0.14969. If you consider Q theoretical, CD we are not considering. If you consider Q actual, CD we are going to multiply. So in this problem, I prefer to find Q theoretical as well as Q actual. And tell me, as per this answer, Q theoretical, whether 0.14969 is actual or theoretical discharge. Find both Q theoretical and Q actual. Q actual will be CD into A1 A2 divided by A1 square minus A2 square under square root into square root of 2GH is the Q actual value. Q theoretical means you cannot consider CD value. So without considering CD value, you will get Q theoretical. So tell me both the answers, Q actual and Q theoretical values. Yes, Q actual is around 0.1466. 1466 is Q actual. Q theoretical, how much you are getting? Okay, Q actual is 0.1466. Q theoretical is 0.149. So in the problem, what mistake I have made is this 0.14969 itself I have written as Q actual theoretical. It should be Q actual. So in the notes, this Q actual, you make the correction. And Q theoretical, write it as 0.14. Q theoretical 0.14969. So in this equation, again you can observe the Q actual will be lesser than the Q theoretical. Okay? Q actual will be less than Q theoretical because in Q theoretical we have not considered the losses. So once you consider the CD value, the value will be lesser than the Q theoretical. Or by this ratio also you can find out CD value. How much is the loss? Loss is around 0.2% or something. Or coefficient of discharge will be 0.98 or something. Okay. So we'll go to again back to the derivation part. So just you can focus on the difference in Venturimeter and orifice that derivation and the change in the design of the orifice meter compared to Venturimeter. So coming to the next orifice meter. So all of you can see here, again a horizontal orifice meter is considered, which is connected between the pipes at inlet and outlet. So flow direction also shown there. In the section one side, the flow is taking place to the section 2. And all, if you see in the orifice in the lab, the connection of that orifice manometer connections, if you see, the one pipe should be at the inlet side of the pipe. Complete pipe can be connected at the section 1, and another tube of the manometer should be connected just after the orifice plate. Why I am calling here orifice plate? Because in entire pipe, the only change in the diameter is with respect to this plate, what is shown with the hatches. This will be having some very small thickness. The thickness of the plate will be very small. The opening of this orifice plate will be exactly at the center. It will be concentric to the pipe itself. And again, the diameter of the opening can be considered as 50% opening with respect to pipe opening. And the pressure drop, if you see here, the flow you can see here, it is not having exactly the converging. It is having gradually decreasing, like a parabolic or some non-linear profile of the flow you can see. Okay, see here, in the first step, if you see, the valve is open and flow starts to flow through the orifice meter. Suddenly what happens, the liquid may be in the, first it is coming and hitting this plate, then at the center it may be flowing continuously. But after some time, if you observe the flow pattern or the flow streamlines, if you see, it will be detaching here. It is detaching and slowly it is following a stream path so that it can touch the orifice plate. And after crossing this orifice plate or the small circular plate, after crossing that, still the diameter of the flow is reducing compared to this orifice plate. So at what point exactly the diameter of the flow is less than the opening of this orifice plate, that point we are calling it as vena contracta. Okay, so exactly after this point, if you see, the distance is around 0.5 of small area. The small area, whatever is there, 0.5 of that area, at that distance, around that distance, you may find out the vena contracta position, or the diameter of the flow is minimum compared to all other diameters. If the diameter of the flow is very small, that point itself denotes as vena contracta point. Then after that, the flow will be accumulating the same diameter of the pipe. Slowly it will come to the complete diameter of the pipe, because openings, it is completely kept open to the full pipe. And due to this sudden change in the diameter, what will happen? There will be no sudden change in the flow also. So the flow will gradually acquire some small diameter D2, and then gradually it will occupy the full space of the pipe. So this needs some space here. Okay, and this space is nothing but the space of pipe itself. It is not the orifice meter. Orifice meter is what? Only this plate, a circular plate. Even by cardboard, if you make one circular hole, that becomes a orifice meter. That's all. That should be placed in a given pipe flow. So sudden change in this diameter, if you do, one can find out the deflection in the manometer due to sudden change in the pressure or sudden change in the velocities. And one can find out the head at what the liquid is flowing in the pipe, and he can find out the discharge. So you can note on this sketch. Derivation, I hope you can take it as homework. I'll just recall the steps of Venturimeter, and I'll explain the difference between the Venturimeter and orifice here in the derivation. So only those differences you can note on in the orifice. Rest all steps are same. So to section 1, the complete pipe diameter is taken. And at section 2 should not be exactly the orifice diameter. This everyone should keep in mind. But in problems, what they do, the diameter D2 will be given directly, opening of the orifice. Many times what they do is, they will take the orifice diameter D2 itself. But actual case, if you see, with losses, with CD value, if you see, the diameter D2 should be considered just after the orifice opening, where the diameter of the flow should be very less. That point is called as vena contracta point. At that point, if you consider, that will give us the actual accurate readings of the discharge. Okay. Now coming to the derivation part. What happened? Pushpa Pujari. Q theoretical is 0.1527. Any others are getting same answer 0.1527? 1527 is little bit higher. Okay, Q theoretical you are getting 0.1527. All of you are getting same. Q theoretical. Q actual is correct. 0.14669. Q actual how much you are getting? Others have got any results in the earlier problem, Q actual and Q theoretical? Q actual is correct or that also should be changed? Q actual we had got 0.14669. Now you are telling Q theoretical 0.1527. Are they both are correct? Or again we need to change this earlier Q actual value? Q actual is 0.14969. 969 Q actual. Yes, all of you change this value Q actual as Q actual, write it 0.14969. And Q theoretical, if you are accepting all this result, all of you, if you are accepting this result, we can write it as Q theoretical 0.1527. Okay, make these corrections. I think today I will not take the problems on orifice or pitot tube. I'll again go back to these problems. Okay, orifice and pitot tube problems, I'll go back. I will make any corrections if possible. Then we'll take these problems on orifice and pitot tube. If any mistakes are there, I'll correct it and come back. Okay. Today we'll take only the last part as orifice meter derivation and problems on that orifice and pitot tube. I'll make the corrections if any corrections are there, like Venturimeter what you have seen, that corrections I'll come out with the corrections and we'll consider in the next class. So I think by going with this Venturimeter 2 problems with corrections, without corrections, I think you might have understood the using the formulas and converting all the values. Okay, that also adds our understanding part. Okay, now coming back to the derivation of this orifice meter. So as I told you, the derivation steps are similar with respect to orifice and Venturimeter. Also, you can recall the equation directly what you have used in the lab. So keeping that in mind, we can again apply the Bernoulli's equation and the continuity equation, and what extra term is implemented or introduced in this derivation, that will focus much. So coming to the Bernoulli's equation for the horizontal orifice meter, again we can cancel this Z1, Z2. So we left with P2 minus P1, sorry, P1 minus P2 by rho g minus velocity square difference divided by 2g. So this P2 or P by rho g, the difference of P1 minus P2 by rho g, we can again represent it as H value, that is the head value. Then here one can find out what is V2 as in the earlier case. So here you can write it as V2 square by 2g equal to H plus V1 square by 2g. Okay. Then one can write down this V2. What may be the V2 value? Velocity at section 2 can be written by using these terms directly. I can write it as square root of 2gh, because 2g is multiplied with h, 2gh plus v1 square. So v1 square, what is happening? This 2g is multiplied with v1 square divided by 2g. So 2g will get cancelled at the with respect to v1 square. So we left with square root of 2gh plus v1 square. So this you can call it as equation 1. Then what we can do is we can go for the finding one more relation, that is the coefficient of contraction for the orifice meter. So in this orifice meter, first thing is we know the area of the opening, A2 is known, but area of the opening at the vena contracta point, if you see this section 2, we don't know what is D2 or A2 at the vena contracta. This point we don't know. So for that, what we are writing here is the ratio of these two values, A2 and A0. Orifice opening A0. Okay. Area of the flow at this point, D2 point as A2. If you take the ratios, I can call it as coefficient of contraction of the orifice. So here it is denoted as CC, A2 by A0, or smaller area by orifice opening. That smaller area is what? The contraction area. This area 2 divided by A0. A0 is the orifice opening. If you take this ratio of these two areas, that can be called as coefficient of contraction. So from this, one can write A2 in terms of this CC. That is, A2 can be written as A0 into CC. So what we did here, before going to continuity equation in terms of A2 we can write it as A0 into CC. A0 is the orifice opening, CC is the coefficient of contraction. This is the new term introduced in this derivation, because here A2 value we need actually, where the outlet flow is coming from the vena contracta, that area is required, because at that point we are finding the mercury manometer head, okay, or this manometer deflection we are finding at that point, section 2, where the small area is possible, that is A2. But in the problems, we know the A1 area, opening of the orifice will be given. But actually, exactly at the orifice opening, we cannot connect the mercury manometer because there is a plate. And also, exactly that point, all the pressure drop is not possible. All the pressure drop is possible at A2. So at that point, we need to connect the manometer. That's why we are taking this A2 in terms of CC and A0. Because A2 is like an assumption here. A2 is somewhere in between. We don't know the area or diameter. So for that, we are writing in terms of CC, area of coefficient of contraction, and area of the orifice, A0. Now come to the continuity equation. So continuity equation, what we are doing again, either you write V1 or V2. So if you write in terms of V1, I can write it as A2 V2 by A1. So A2, what I'll do from this coefficient of contraction only in the orifice meter. This coefficient of contraction, using that relation, I can write A2 as A0 into Cc into V2 by A1. So this equation you can call it as equation number 2. This I am writing in terms of V1. Why it is required? The continuity equation V1 is required for substituting in the equation number 1, that is Bernoulli's equation. I want to substitute in V2 formula. To put this V1 term or A0 Cc V2 by A1 in V1 square of the equation 1. So what I'll get now? I can write it as V2 square as 2gh plus A0 by A1, A0 by A1 square, Cc square into V2 square. So you can write down this whole equation, V2 square as this whole term. You can write down. Then as you know, we have to take for square root on both sides. Now you take the square root, I can write V2, okay, V2 as final equation, square root of 2gh divided by square root of 1 minus A0 by A1 square into Cc square. Or what you can do is, we can club the common terms. What are those common terms? V2 square is the common term. So if I take V2 square on one side, 2gh on one side, what I can write? V2 square minus this A0 by A1 whole square, Cc square into V2 square equal to 2gh. Okay, again same thing. Take the V2 square common, then I can write it as 1 minus A0 by A1 whole square Cc square. Okay, that is equal to 2gh. Now I can write V2 equal to, see this should be V2 square. So there is a mistake in this step. You write V2 square in the earlier step. Here, while writing square root of 2gh, you write V2. V2 can be written as square root of 2gh, okay, square root of 2gh divided by this bracket, complete bracket I'm taking in square root. So now I got value of V2 in terms of area and Cc. So taking this V2 and assuming A2 value, okay, assuming A2 means A2 we don't know. So we are writing A2 in terms of A0 into Cc into V2. A0 into Cc into V2 value. Okay. Now coefficient of contraction, that Cc, if you recall, that is a ratio of area at section 2 to the area of orifice opening, that is A0. So if you equate these two terms, Cc and Cd, one can write it as Cc as Cd into square root of 1 minus A0 by A1 whole square into Cc square divided by square root of 1 minus A0 by A1 whole square. So this we will get by considering these two relations. That is, Cd can be given as Q actual by Q theoretical. Okay. And Cc, we know that it is a ratio of A2 by A0. Or you can take the ratio of Cc by Cd, and you can write it as square root of 1 minus Cc square into bracket A0 by A1 whole square divided by square root of 1 minus A0 by A1 whole square. So from this, one can note down how to replace this Cc value with respect to Cd value. So that Cc value we are replacing with Cd into square root of 1 minus A0 by A1 whole square into Cc square divided by square root of 1 minus A0 by A1 whole square into V2. And V2 from the earlier equation we found out, that is square root of 2gh by square root of 1 minus A0 by A1 whole square Cc square. If you substitute, we can cancel some of the terms. We can cancel this So what all things we can cancel? Cd into A0 square root of 2gh divided by square root of 1 minus A0 by A1 whole square. So I have cancelled here Cc square. Okay. Cc square is cancelled. Then A0 is also cancelled. So after cancelling Cc, now one can write it as Cd into A0 into A1. So all the numerator terms you can take it to the top side, that is A0 square by A1 square, and square root you can take A1 at the top. That will become Cd into A0 into A1 square root of 2gh whole divided by square root of A1 square minus A0 square. So just to differentiate from orifice and Venturimeter, we have taken capital A for the orifice meter. And here A1 is at the inlet side, A0 is the orifice opening, not the section 2. From the section 2 considering Cc, we have written in terms of Cd and A0. So finally, we can write it as Cd into A0 A1 square root of 2gh divided by square root of A1 square minus A2 A0 square. So this will give us the actual discharge from the orifice meter. And if you not consider the Cd value in the same formula, this will give us theoretical discharge of the orifice meter, where A1 is the inlet area, A0 is the area at the smallest diameter. That's the vena contracta. At that point, if you consider that area, we have considered as A0, not the A2. If you consider A2, then you have to write the formula in terms of Cc. Okay, coefficient of contraction you have to write. If you consider A0, then you can write the formula in terms of Cd. So coming to the next class, all of you just recall the difference in this equation with respect to the equation which is used in the lab. If they both are same, both are different. If they are different, what is the difference in different parameters? Okay, and I'll come up with the corrections in these problems. If any corrections are there in this next problems, then we'll take the next syllabus in the next class. See, one more thing. What is the question? IA portion. See, IA portion is up to pressure measurement, up to the manometers. Unit 1 full, properties of the fluid, full unit. And in unit 2, up to the pressure measurement. Up to manometers you have to study. Then later hydrostatic, I think 1 minute. I'll open the syllabus itself. And one more thing, on Wednesday morning, I have invigilation duty from 10 to 12. So better will again this week also will keep the class on Friday 10 to 12. Okay, just inform all the students and any other staff also planning the classes. You just inform them. Our next class of FM will be on Friday 10 to 12 because I have invigilation duty of fifth semester on Wednesday, so I cannot take the class. So syllabus for first IA, you can note down. That's fluid statics, sorry, unit number 1, this is full, properties of fluids. Then in this, fluid statics, Pascal's law, differential manometers, uh, total pressure force. This I will tell you later, okay, whether it is kept for the IA test or not. So until this differential manometer you keep prepared, before second next class or the in your group, I'll mention these details, whether this part will be kept in this IA test or not. But buoyancy from this part will not be there in the second first IA test. Is that clear? So up to differential
Yes,
manometer, keep prepared and ready. Okay. Okay, I think we'll stop the class here. We'll meet on Friday.